Well, I'm very happy to welcome Laura Howe to speak to us this morning. Laura is a reader in epidemiology and medical statistics at the University of Bristol, and her two main interests are firstly the life course epidemiology of obesity and cardiovascular disease, and secondly the complex and bidirectional relationships between social factors and health. So today Laura is going to talk about her use of Mendelian randomization to explore the causal associations between health conditions and health behaviours and social and economic outcomes. So as Bridget said, please do feel free to add your questions or mention that you have a question as we go through the talk, and then we'll go through these at the end of the presentation. So great, over to you, Laura. Thanks very much.
Thanks very much, Eleanor, and thank you for the invitation. So I'll just try and share my screen. Okay, is that coming up?
Looks good.
Perfect.
Yeah.
Excellent. Okay, so yeah, thanks very much for the invitation to present today. It feels a little bit strange presenting to nobody, but hopefully you're there listening. Okay, so as I'm sure you're all aware, there's a vast body of literature demonstrating influence of social and socioeconomic factors on health, and showing largely that there are huge socioeconomic inequalities in health. The focus of this project was to look at whether the reverse is also true, and whether there is what's sometimes called health selection, i.e. whether poor health limits people's abilities within their social life, their school life and their work life. But if we want to study the social and socioeconomic consequences of health, this is fraught with methodological difficulties. Because of those strong influences of socioeconomic factors on health, if we come to study the knock-on effects of health to socioeconomic conditions, we're going to have huge confounding by kind of prior or earlier life measures of social and socioeconomic factors. So traditional epidemiological methods for this topic just don't really cut it. We're going to have massive residual confounding. So what we are doing in this project is using Mendelian randomization, which is where we use genetic information as a tool to try and strengthen causal inference. So within Mendelian randomization, we're not interested in the genes per se, we're using them as a tool to understand an exposure outcome relationship that we're worried might suffer from confounding and reverse causality. So a few kind of core principles that underlie the use of Mendelian randomization. Firstly, that your genetics are determined at the point of conception and therefore cannot be influenced by the social environment in which a person lives. And secondly, that the genes you inherit from your parents are random. That is, of course, conditional on your parents' genotypes, and that's something we'll discuss a lot more later in the presentation. So therefore, if we're using our genetics as a tool to proxy for our exposure of interest, our estimates shouldn't be vulnerable to either reverse causation or to classical sources of confounding that we're familiar with in epidemiology. So this kind of quasi-random assignment of genetics can be sort of considered a natural experiment, and it's sometimes compared with an RCT. So in a randomized trial, we assign people to one exposure or another exposure, or one level of an exposure or another level of an exposure. And in Mendelian randomization, we're assuming that people have a random assignment to a genetic propensity for their exposure. So I'll try and explain this in pictorial form, and then I'll use a DAG to show you a different way, just to kind of help people try and understand the method who think in different ways. So if we focus here on the left-hand side at the top, this is our general population. And in this example, we're interested in the effect of BMI on systolic blood pressure. And here in our population, we're going to assume that we've got a confounding factor, perhaps socioeconomic position. And each shape within this general population represents a different level of socioeconomic position, so a different level of our confounding factor. We move down here to panel 2. we're now going to sort people according to their genetic propensity to high BMI, ranging from the pink people here who have very low genetic propensity to high BMI, up to the dark blue people here who have very high genetic propensity to BMI. But we should have, if our assumptions of Mendelian randomization are correct, we should have no relationship between that genetic propensity to BMI and our confounder, which here is socioeconomic position. So you can see here in this picture that the shapes are equally distributed across our levels of genetic propensity to high BMI. So then moving on to panel 3 up here in the top right, if we sort people according to their genetic propensity to high BMI, that should relate to their measured BMI. If it doesn't, then we haven't got a good set of genetic variants and it's not useful to us. So this is just a test that as we move from low genetic propensity to high BMI up to high genetic propensity to BMI, we should see a pretty decent relationship with measured BMI. And then here down in the bottom right, this is really the crux of what Mendelian randomization is doing. Now, we keep sorting people according to their genetic propensity to high BMI on the x-axis, but on the y-axis, we put our outcome of interest. Here, our measured risk of hypertension. And here in this example, we're seeing that as genetic propensity to BMI increases, so does our risk of hypertension. So we can take this as evidence that BMI has a causal effect on hypertension that isn't affected by our confounding factor, here socioeconomic position, which is unrelated to our exposure here. So to put that in slightly more formal terms, this is the DAG, the directed acyclic graph of what's going on in Mendelian randomization. So we've got our exposure X and our outcome Y, and we're using our genetic information here, Z, as an instrument. So for those of you who have studied any economics in the past, you may be familiar with this diagram because the method that Mendelian randomization is using has a long history in econometrics, and it's called instrumental variable analysis. So economists have used this approach for a long time using non-genetic instruments. So some of the assumptions we're making here is that Z is related to X, but that it's only related to our outcome Y through X. So there's no pathway going from Z to Y other than the path through X, and it's unrelated to our confounders. A couple of key assumptions. The first is about pleiotropy. So this is what I just said, the assumption that there's no pathway from Z to Y other than going through X. So there's no influence of our genetics on our outcome that doesn't operate through the exposure we're interested in. It's absolutely fine if Z affects something which affects X. That's called vertical pleiotropy, and that doesn't matter for Mendelian randomization. That doesn't violate our assumptions. There's now a wide range of statistical tools to kind of test for horizontal pleiotropy and see whether this is likely to be influencing the findings. A second key assumption is that the SNP is single nucleotide polymorphism. It's just a particular term for a type of genetic variant. So we're assuming that our genetic variants are randomly assigned across the whole population. And as I mentioned earlier, we'll be talking about this at length later because we've got some data to show in some circumstances this can lead to bias in MR. So the project that I'm talking about today as a whole is looking at the social and socioeconomic effects of health defined very broadly, so looking at a range of health conditions and health behaviours. But for the first, for the bulk of the presentation, I'm going to focus on obesity, or more accurately, BMI as a continuous measure. And there's good reason to think that obesity could have an effect on social and socioeconomic outcomes, because we know that people who live with obesity are more likely to suffer from stigma, from discrimination, low self-esteem, depression, and poor physical health. And all of these could have a knock-on effect in people's social life, their experience at school, and their experience in the workplace and the job market. So the first set of results that I'll show you are from UK Biobank, which is a very large sample of adults in the UK. So 500,000 in the whole study, but 350,000 once we restrict to white British ancestry, which is necessary for the main genetic analysis, and those with genetic data. So the participants of UK Biobank were 40 to 69 years at baseline. And here we've looked at BMI in relation to 6 different measures of socioeconomic position. So Townsend Deprivation Index, which is a measure of area level deprivation, annual household income, job class, so looking at occupational social class and comparing skilled versus unskilled professions, employed versus unemployed, years in education as a continuous measure of educational attainment, and then degree level education versus lower as a binary measure of educational attainment. And we've also looked at 4 measures of social connectedness, all of which have been shown to be associated with health outcomes in previous literature. So firstly, whether people are in a cohabiting relationship. Secondly, how frequently they have visits or contact with friends and family. And we've dichotomized that as weekly or more versus less than weekly visits. Participation in leisure or social activities, and that was dichotomized as any participation versus no participation. And then how often people are able to confide in others, and that was dichotomized as less than weekly versus weekly or more. So here are some results. I'll talk you through them bit by bit. So here at the top on the left, we've got Townsend Deprivation Index, so our measure of area level deprivation. And this first point is the observational ordinary least squares analysis. And the second point is our genetic analysis using Mendelian randomization. So both of those analyses suggest that higher BMI leads to higher levels of deprivation, i.e. lower socioeconomic position, with very similar point estimates between the traditional and the genetic analyses, but you get much wider confidence intervals in the MR because it's a more power-hungry type of analysis. The next result down is looking at income, so that's another continuous measure. And again, the observational and the genetic Mendelian randomization analyses both suggest that higher BMI is related to lower income. Years in education, the same story, but here our point estimate is attenuated quite a bit in the Mendelian randomization analysis compared to the observational analysis, suggesting perhaps that the traditional analysis was more affected by confounding than some of the other socioeconomic outcomes. Then on the right-hand side of the slide, we've got degree as a binary outcome, job class and employment. And all of those observationally show relationships with higher BMI to worse outcomes. The MR was consistent with that for degree and for the binary measure of job class. For employment, the point estimate was pretty similar, but the confidence intervals were very wide for the Mendelian randomization analysis. Now the social outcomes, there was a lot less going on in the Mendelian randomization. So observationally, BMI was related to all of these measures, not always in the way that you might have hypothesized. So for visits from friends and family, it went that higher BMI was related to more social contact, whereas for participation in social activities and having someone to confide in, higher BMI was related to lower levels of social connectedness. But the Mendelian randomization analysis results for most of these outcomes have pretty wide confidence intervals that span the null. Just to focus in on that last one, cohabitation, and so I think this is quite an interesting finding from this study. Here, if we look at the sex stratified results, because they're particularly interesting for this outcome, and there was very strong evidence of a sex interaction here. In men, both observationally and genetically, higher BMI was related to higher odds of being in a cohabiting relationship, although the confidence interval was pretty wide for the Mendelian randomization analysis. Whereas in women, the opposite was true. Both observationally and genetic analysis suggested that higher BMI was related to lower odds of being in a cohabiting relationship. And this is really interesting and quite depressing, really, in terms of that it links quite neatly in with lots of sociological literature, talking about kind of sex-specific cultural expectations of body size, and how potentially a larger body size is seen as a kind of signal of strength in men, but not seen favourably in women. And this is consistent with other study designs that show a greater degree of weight stigma in various circumstances and settings for women. So we also used a fairly new method which enables you to look at non-linear relationships within Mendelian randomization. So here, this was trying to look at the idea that observationally you sometimes get this kind of J-shaped or U-shaped relationship, such that both low BMI and high BMI are related to adverse outcomes. And indeed, we did find that the Mendelian randomization results supported that for both Townsend deprivation and for income. So here there was an effect of both low BMI and high BMI being disadvantageous for those outcomes. For the other socioeconomic measures, we didn't see any evidence of nonlinearity, but for the binary measures, power for these nonlinear results is quite low, so that we can't be too sure of what's going on there. The cohabitation results showed some interesting nonlinear effects as well, and particularly again here, if you look at the middle and lower panels there to focus on the sex stratified results, in the men there was really strong evidence of an effect of low BMI lowering the odds of cohabitation. So these graphs are, I think, a little bit tricky to understand at first glance, because in the low BMI group, that's saying that higher BMI is related to higher odds of cohabitation. So it's evidence that low BMI is related to lower odds of cohabitation. In the men, there wasn't much going on at the higher BMI ends. There's a little bit for the very high BMI groups, but not a clear linear pattern across those deciles of BMI there, deciles of genetically predicted BMI. In the females, it's the opposite. There's not much going on in the lower BMI groups, perhaps a little sign of some effects of lower BMI being related to lower odds of cohabitation, but not very strong. Whereas for the higher BMIs, there's this kind of increasing linear trend towards higher BMI being related to lower odds of cohabitation. So I'll just touch very briefly on a kind of another strand to this project where we broadened the range of health conditions and behaviours that we were looking at. And we looked here at a few different health behaviours. So in addition to BMI, we looked at alcohol intake and smoking. And we also looked across a range of health conditions. So asthma, breast cancer, coronary heart disease, depression, eczema, migraine, osteoarthritis, and type 2 diabetes. And there are a couple of other kind of continuous risk factors in there as well, cholesterol and systolic blood pressure. And this graph shows a heat map of p-values, with the darker the colour, meaning the smaller the p-value, so the stronger the evidence. So the take-home message here really is that there's quite a bit going on for alcohol intake on the left, particularly with the socioeconomic outcomes, not so much with the social outcomes. Quite a bit going on for BMI, and quite a lot going on for smoking, but really not much else across the board. So for the health conditions, there were a couple of results for asthma and eczema, most of which were so extreme that we think they're not real, that they're likely to be driven by pleiotropy, to do with something to do with kind of autoimmune genes picking up something a bit funny. But for the other health conditions, really nothing much going on at all. So higher BMI, alcohol intake and smoking were all estimated to adversely affect a range of outcomes, but for health conditions, we didn't find very much at all. And it might be that there really is nothing going on, it might be that there's selection bias given the relative health and age of the participants in UK Biobank, or it could reflect a lack of power to detect effects, given that for the health conditions, the genetic risk scores tend to be a lot less strong than for the risk factors like BMI, alcohol and smoking, where we've got quite a large number of genetic variants now. However, I think it's also worth reflecting on just the study design as a whole. And this study design kind of works quite well for these continuous measures, BMI, alcohol use, smoking, which kind of affect you cumulatively across a life course. Whereas for health conditions, particularly for something like coronary heart disease or a cancer, where it might be a time-limited event, I suspect that looking at this kind of lifetime average approach that Mendelian randomization is trying to estimate isn't probably the right method to use for that question. You probably there want people, you need to think about the timing of event in relation to changes in income and work and things like that. So I suspect that if you looked more carefully at longitudinal data, that would probably be more appropriate for those questions. Within this project, we've also done some analysis of ALSPAC, which for those of you who aren't familiar with it is a birth cohort study based around the Bristol region, and the participants are now in their late 20s and early 30s. And here we wanted to look at a range of child onset health conditions. So we had ADHD, depression, autism spectrum disorders, migraine, asthma and BMI. And we related those to performance in GCSEs, so GCSE point score as a continuous measure of educational attainment at age 16, and also to school absence between the ages of 14 and 16. So here the same approach, we used the genetic variants for each of those conditions and looked at their association with the outcomes. And here we found evidence that both ADHD and BMI genetic risk scores were related to lower educational attainment, but that only the BMI polygenic score was related to school absence. However, some really big caveats to all of these results is that we've recently been doing some analyses looking at some of the biases that we've known have been theoretically possible within Mendelian randomization, but haven't had the data to actually explore until very recently. So this, if you're interested in this, this is a paper that's just recently out in Nature Communications that I'd recommend you have a read of. So things that can bias MR. So I don't know if you heard population stratification, but this is where gene frequencies differ between ancestral populations, but so do environmental and cultural factors. So this can produce spurious associations and a classic confounding problem. So we can adjust for principal components to try and address this, but we can still get residual confounding even if we do that. So the second thing that can bias Mendelian randomization is dynastic effects. And this is where parental genotype can influence offspring phenotypes via environmental pathways. And this is a really interesting concept. And for those of you who are interested, there was a brilliant paper came out a couple of years ago by Kong et al. Called The Nature of Nurture. So the idea here, if we think about our specific example, we're interested in whether a child's polygenic score for BMI influences their educational attainment. So that could be through processes operating at the child level. For example, the child's BMI leading to them being more likely to be bullied at school or similar mechanisms. But you can also imagine how parental factors could influence this. So if the child has a high genetic propensity to BMI, so do their parents, or at least one of their parents. So it's possible that that parent's high genetic propensity for BMI influences their own BMI, which influences their own health, for example, and therefore their ability to do as well as they might do in the work environment. And that lack of economic resources could influence the child's educational attainment. So again, it's a kind of classic confounding problem within epidemiology, but the confounding here is intergenerational confounding. Finally, another source of kind of family level bias in Mendelian randomization is assortative mating. So this is where people form partnerships with other people who are more similar to them than dissimilar. So non-random partnership formation. So if we have non-random partnership formation in the parents' generation, according to traits that we're interested in our analysis, this can again induce confounding. So here we know that we do get assortative mating according to both BMI and, probably more importantly, educational attainment. So a solution to this is to combine within family methods and Mendelian randomization methods. So historically, people have used family analysis to try and strengthen causal inference, because if you compare two siblings who are discordant for your exposure, you know that by and large their family environment is shared, so you should be kind of controlling for their family environment in some way. So within family Mendelian randomization, either again comparing siblings or looking at analysis within mother, father, child trios, where you've got genetic data for all three of those people, if we apply Mendelian randomization approaches within these designs, they should not be affected by population stratification, by dynastic effects, or by assortative mating, because parental genotype is held constant in these approaches. So until recently, we've not been able to do this because we haven't had large enough samples of data with siblings or with family genetic data, but these data are beginning to become available. So for our BMI analysis, we tried to do this within UK Biobank, where there are about 39,000 siblings from 19,000 families. And here we've got, so on the left, Townsend deprivation index, in the middle income, and on the right cohabitation. And then going down the results, we've got the main MR analysis in unrelated people. Then we carried out MR analysis in those 39,000 siblings, just to check that they weren't a kind of unusual group of participants. And then the final point on the plots is within sibling MR analysis, so combining the within sibling data and a Mendelian randomization approach. And for both Townsend deprivation index and income, what we see is that the effect estimates are attenuated right towards the null in those within family MR estimates. And in fact, for income, the coefficient actually flips to the other direction. But here in UK Biobank, with this sample size, our confidence intervals for the within family estimates are huge, because these methods really require more data than we have here. For cohabitation, I think the results are really interesting. So if we look at the sex stratified results, the men in the middle and the women at the bottom, the within family MR analysis, the point estimates are in the same direction as the main analysis, but actually stronger. And our confidence intervals are pretty wide, but I would say tending towards suggesting that those results may be real and unaffected by those family level biases. Since we did that analysis, there has been more data become available. So this Ben Brumpton's paper, just published this year, combines data from UK Biobank and Hunt, which is a Norwegian study. So now there are almost double, about 61,000 siblings within this analysis. And here, Ben looked at a few different outcomes. So BMI as our exposure here, and diabetes as our outcome. If you just focus on those 3-point estimates in the green box at the top. So here we're looking at BMI and diabetes. The top estimate is our MR in unrelated participants, in 350 participants. And that shows, as you'd expect, an effect of BMI on higher risk of diabetes. You restrict that analysis to the 61,000 siblings and you see the same thing. And then if you do your within family Mendelian randomization in those siblings, you again see a similar thing, slightly higher point estimate, wide confidence intervals, but supporting a causal influence of BMI on diabetes risk. Moving down, now we're looking at the effect of BMI on high blood pressure. And again, the within family Mendelian randomization supports the causal effect of BMI on high blood pressure. Now, if we look at height as an exposure and education as an outcome, our Mendelian randomization in the top of that green box suggests that taller height gives you an educational advantage. When we do MR within those, standard MR within those 60,000 siblings, we still see evidence of an effect of taller height on higher educational attainment. But when we do our within family Mendelian randomization on that sample, the point estimate goes right down to the null. Our confidence intervals are huge, but our point estimate is smack bang on the null. And then back to the question that we were interested in, whether BMI has an effect on education. Again, our MR in unrelated individuals in the top of the green box suggests that higher BMI is associated with lower educational attainment, and the same within our sample of siblings. But again, once we apply our within family Mendelian randomization, the point estimate goes right to the null with very wide confidence intervals. And within this paper, Ben also managed to replicate these results in more than 200,000 siblings from 23andMe. And for both height and its effect on education and the effect of BMI on education, the point estimate was bang on the null with very precise confidence intervals now because the sample size is very big. So this is suggesting that our hypothesized effect of BMI on education is driven primarily through those family level influences that we think are leading to bias in our classical MR of unrelated individuals. So we are taking this forward by using some trio data, some mother, father, child trios in a Norwegian birth cohort. And we've got, I think, about 15,000 trios at the moment, hoping to increase to about 80,000 eventually. And we're looking both at the effects of BMI on education, but also BMI on depression to see whether that holds up to the influence of these family level biases. So just to finish, some thank yous, particular thanks to Mandy Hughes and Sean Harrison, who have done a lot of the analyses I've presented and who I've stolen slides from. Also to Neil Davies, who's leading the within family analyses, and Suggest Tyrrell from Exeter, who did most of the BMI analysis in UK Biobank. And a thank you to my funders. The Health Foundation fund this project, and the MRC fund me as a fellow. So thank you very much, and thank you to those of you who bore with me through the technical difficulties.